My own recommendation, in principle, is that this anthropic explanation is called, that is, using the idea that life exists as a criterion for separating out physical systems. My recommendation is these anthropic explanations should be considered an explanation of last resort, by which I mean that it's very hard to confirm such an explanation, and basically we should accept such an explanation only if we are really sure that we can't find a better explanation. And therefore the anthropic arguments only become attractive when the search for more deterministic explanations have failed, and that so far at least has been the case for the cosmological constant. So is it time to accept this explanation of last resort? I think the best thing I could say about that is simply that your guess is as good as mine. You can decide for yourself if this explanation makes sense. Nobody really knows. But certainly for the cosmological constant, I think it's hard to find any other explanation. And so far, I would say that it's pretty clear that this selection effect explanation really is the best explanation we know for why the cosmological constant is so vastly smaller than naive theoretical expectations. So I think it's certainly time to consider it. And perhaps another road sign by Andrew Chamblin is relevant here. That's Andrew's sign's opinion, at least, of how the story rates. Maybe it is just a dream to think that this is the right explanation. Nobody really knows. It is disappointing if this is the right explanation. And this, I think, is my last significant slide, and then I'll be summarizing. In the early time of string theory, people were, at least many people, were very optimistic that string theory would be able to tie together everything we know about the universe and give us an explanation for the way what we call the standard model of particle physics works. We have this thing called the standard model of particle physics, which so far really explains every particle physics experiment that we know how to do. That should change soon at the LHC, where they can get to higher energies where we're really not sure what we should expect. But at the energies that have been reached by accelerators for the past 30 years, we really have one theory that can explain all the results that have been seen. And that's called the standard model. It has like 20 free parameters in it, 20 numbers like the charge of an electron or the mass of an electron, which the theory doesn't predict. You have to measure. And the hope was that maybe string theory would give us the values of these free parameters. But if this landscape idea is right, those hopes are really dashed. They would be different in every pocket universe. And you could really only talk about what you're likely to observe by talking about overall probabilities in the entire multiverse and by trying to understand the probabilities of forming different pocket universes and so on. And it would get very complicated, and there would really just not be a unique answer. Roughly speaking, we would be saying that things like the mass of an electron are not really fundamental constants at all, but really just properties of the 1 of the 10 to the 500 different vacua that we happen to be living in. Now, this is not the first time something like this has happened in science. So maybe it's happening again. There is a precedent for it, probably many precedents for it. One precedent that people often talk about is Kepler and the radii of planetary orbits. It's hard to put our psychology back into the time of Kepler, but you could try to do it. Remember, from Kepler's point of view, the heavens consisted of the solar system, or at least the part of the solar system that was known then, and this sphere of fixed stars that went around in a circle. And the fixed stars weren't very interesting because they just went around in a circle. The interesting thing was the planets. And to Kepler, that really was the universe. And Kepler spent a lot of time trying to understand what to him was a very fundamental property of the universe, which are the radii of the different orbits of the planets. And you've probably read in history books that he constructed a complicated model of nested solid, regular solids to try to explain why the orbits of the planets had the radii that they have. And he was frustrated because he was never able to get this to quite work. And he thought that, gee, the orbits of the planets is really fundamental science. Why doesn't it fit this model of the nested regular solids? From a modern perspective, expecting the planets to fit some model involving regular solids sounds totally absurd. We know that regular solids have nothing to do with the formation of planets. Planets are formed from protostellar disks and so on by a process of evolution that we think we crudely understand. And the radii of the orbit of any particular planet is essentially a random number determined with some probabilities, but not by any fundamental laws of physics. So if this landscape idea is right, the charge and mass of an electron will fall into the same category as the radius, for example, of the Earth's orbit around the sun. It's really just due to some historical accident and not due to any fundamental principles that we should try to understand. So that's the picture that's being suggested here. And it's not clear really if that's the right picture for us to adopt or not. So let me now just sort of summarize what I've said, and then I'll stop. I've tried to explain that the inflationary paradigm is in great shape. This theory of cosmic the theory of cosmic inflation can explain the large-scale uniformity of the universe. It makes a prediction for the mass density of the universe, which we now know is accurate to better than 1%, and explains the ripples that we see in the cosmic background radiation in terms of assigning the origin of those ripples to quantum fluctuations, which is kind of mind-boggling to think that the Andromeda galaxy is a quantum fluctuation. But that is the picture, and lo and behold, it seems to actually work. Now, we've seen evidence for this idea of a multiverse. It's certainly not proof. I would describe it in summary as kind of three winds that are all blowing in the direction of the idea that this multiverse might describe the system that we actually live in. First of all, we now know that almost all, not quite all, I have to admit, but almost all inflationary models seem to be eternal, and that they have the property that once inflation starts, it never stops. But rather keeps on going, inflating forever, producing an infinite number of these pocket universes. It's also the fact that string theorists mostly agree. I only know a few who think otherwise. String theorists mostly agree that string theory has no unique vacuum, but rather has a landscape of 10 to the 500 or more different long-lived metastable states, any one of which can act like the vacuum within one of these pocket universes. And they would all have different vacuum energy densities. So some of them would be as small as what we observe, even though most of them would not be. And finally, astronomers have put all this together by discovering that the universe is accelerating. That in turn implies that there's some vacuum energy that's non-zero. At least that's the most simple explanation. But nonetheless, this vacuum energy is vastly smaller than what we would expect by our understanding of particle physics. So one way of explaining that is this anthropic explanation, the explanation which holds that indeed it's only a tiny fraction of the pocket universes which have vacuum energies that are this small, but that's exactly the place where we'd expect life to be formed. So that's where we expect us to be, and therefore we think maybe we can understand why it is that when we look at our visible universe, we observe it to have this incredibly small vacuum energy. Whoops. So the bottom line is that we've really never had a model of the universe that works so well, and that we really can explain quantitatively the homogeneity of the universe, the mass density of the universe, and the spectrum of density fluctuations. But nonetheless, it fundamentally relies on this issue that we don't understand very well, this issue of dark energy. So finally, I think one of Andrew's signs gives us a final answer here. I know both what you know and what you don't know. And what we need to do is to find the author of that sign and ask him and get all of this settled. But otherwise, it's kind of a mystery to know where we should be going here. Thank you.
Thank you very much, Dr. Guth. We have time for probably one or two quick questions if people have anything on their mind. If you could raise your hand and I'll bring the microphone to you so we can all hear. Otherwise, if you are a little embarrassed, Dr. Guth will be